Here's a video that will help us do some of the applications of the related rate problems using trigonometric derivatives. So this is question number 12 from the back side of the first worksheet. And in question number 12, it says a ladder 10 meters long rests against a vertical wall. And the bottom of the ladder slides out at 2 meters per second. So here's the ladder. This is the wall right here, and they give us dx over dt equals 2 meters per second. So clearly a related rate question. They've given you a rate of change. X is getting bigger at this rate. And then it says, how fast is the angle between the top of the ladder and the wall changing when the angle is pi over 4? So as x slides out, theta gets bigger, and they want us to find d theta over dt. So we're going to look at our diagram, and we see theta, x, and 10, and we can use a trig ratio to compare those three. So we can say the sine of theta is equal to x over 10, opposite over hypotenuse. You could leave it like that. You can cross multiply and say x equals 10 sine theta. So you've got a formula with x and theta in it, and those are the two rates that we are given. So let's take the derivative of this with respect to time. Related rates are always d over dt. So we have dx over dt equals, the derivative of sine theta is cos theta, so 10 cos theta times d theta over dt, and that is the derivative of the argument. Now let's see if we can find the when. It says when theta is equal to pi over 4. Well, what happens when theta is equal to pi over 4? Let's see if we can find our value. Dx over dt, 2 meters per second, we'll just put the number 2 in there, equals 10 times the cos of pi over 4 times our unknown value, d theta over dt. Well, according to our special angle triangle, the cos of pi over 4 is 1 over root 2. 1 over root 2. 2 is equal to 10 times 1 over root 2 times d theta over dt. So we're going to take and multiply both sides by root 2 and divide both sides by 10, and we'll get 2 root 2 over 10, which is equal to root 2 over 5, and that's d theta over dt. The next question I wanted to look at the same page was about a revolving spotlight. So take a look at this. This light is shining on the shoreline down here. It's 925 meters away from the shore. And as it rotates, the image of the light shining on the shore keeps going down further and further and further. And so that this distance right here keeps getting longer and longer and longer, and the light rotates, and then eventually it'll spin around and come back to its starting point. But imagine it's going down the shore, and you see this distance getting longer and longer and longer like that. So they give us d theta over dt, and it says that it revolves 2 revolutions per minute. Well, we're going to times that by 2 pi, since 1 revolution is 2 pi. 2 revolutions will be 4 pi radians, if you like, per minute. That's d theta over dt, how fast this angle is changing. And the question they ask us is, as it goes down the shore, at what rate is it going to change? Let me just double check the words in the question here to make sure I've got it right. How fast does the beam sweep along the shore at its nearest point? We're going to answer that question. Then it says, how fast does it sweep along the shore at a point 1275 meters from the nearest point? So let's start by setting up our triangle again. We've got theta x, the opposite side, and 925, the adjacent side to theta. So we can say that the tan of theta equals x over 925. And as we cross multiply, x is equal to 925 tan theta. And they ask us, how fast is this changing? Dx over dt equals question mark. So let's take the derivative of this with respect to time. Dx over dt equals 925, and the derivative of tan theta is secant squared theta times d theta over dt. So they give us two whens. The first when is when nearest when it's at the nearest point. And the second when is when x is equal to 1275. So let's try this one right here. We can set up our right angle triangle like this. 925 here, 1275 here, and we'll use Pythagorean theorem to find this value right here. Let me grab a calculator and do that. So dx over dt is going to equal 925 secant squared theta times d theta over dt is 4 pi. Let's take a moment. Let me grab my calculator and see if I can figure out that missing side. 925 squared plus 1275 squared. So we get this value right here to be the square root of 2481250. So dx over dt equals 925 times, and secant of theta is going to be hypotenuse over adjacent, square root 2481250 over 925, and all of that is squared, times 4 pi. So I don't have space or time to simplify that, but when you do, you'll get your answer, dx over dt, and it will be in meters per minute. The next question I'm going to try is number 11. And in number 11, they give you two sides of a triangle, 8 meters long here, 6 meters long here, and this angle keeps getting bigger and bigger and bigger. And as that gets bigger and bigger and bigger, it makes the height taller, and it's going to change the area of the full triangle. Theta is changing at 0.035 radians per second, and they say, how fast is area changing? So let's consider how we can find a ratio with height in terms of theta. So looking at this little right angle triangle that I've created, you can say that the sine of theta is equal to opposite h over the hypotenuse for this right angle triangle, 6. So h equals 6 sine theta. And that's good because now we can establish our area formula in terms of theta and not in terms of h. So let's take a look at our formula for area. Area is equal to 1/2 the base times the height. Well, the base of this triangle is always 8. And the height of the triangle now we can express as 6 sine theta. So area is equal to 24 sine theta. Now we have a formula with theta in it and a in it for area. And we're going to take its derivative with respect to time. dA over dt equals 24 cos theta times the derivative of the argument, d theta over dt. And what was the when in this question? In number 11, when theta equals pi over 6. So you've got dA over dt equals 24 cos pi over 6 times 0.035. That's d theta dt. So look at your special angle triangle. 2, 1, root 3, pi over 6. And we're looking for cos. So we've got dA over dt equals 24 cos of pi over 6, root 3 over 2, times 0.035. And that will give you dA over dt in meters squared per second. Going to the front of that page, we'll take a look at question number 3. And number 3 has an interesting math principle that you might not be aware of. So in question number 3, we want to maximize the area of this triangle that's inscribed inside a semicircle. Well, when you take a triangle and inscribe it inside a semicircle, it means that you're using the diameter as the hypotenuse, and then you're taking and going from B to some point on the semicircle and then back to the other side of the diameter. Well, if you inscribe a triangle on a semicircle, this angle will always be 90 degrees. So that means that we can use this as A and B, two sides of the right angle triangle, and we know theta is going to be this angle over here. So what size should we make this angle to maximize this area? Let's take for a moment and think about what another triangle might look like, and then I'll erase it. So we might draw a triangle that looks like this. And what we know to be true is that this angle up there is going to still be 90 degrees. This would be A and this would be B. Which of these two triangles has the biggest area? Or someplace in between, we'll have to decide. So let's look at the red triangle. And let's see if we can get the sides in terms of theta. So what about sine theta? Well, sine theta would be opposite A over 10. So that means A equals 10 sine theta. And what about the cos of theta? Cos of theta is equal to adjacent over hypotenuse. Cos theta. And so now we have the two sides of the triangle that we're going to use to calculate the area in terms of A and B, in terms of theta. So area is equal to 1/2 the base times the height. Let's imagine this to be the base. So we've got A equals 1/2 of B. I guess we could use this one as the base, 10 cos theta, times the height, 10 sine theta. Those ones are interchangeable. As you multiply that out, you get A is equal to 50 sine theta cos theta. So we can take that right now and we could take the derivative. Now notice this one is a max-min, not a related rate, so we would take dA over dt, but A prime. So you could do that as a product rule. Another alternative would be to take this one and simplify it this way. So still A, we would say it's equal to 25 times 2 sine theta cos theta. And the reason we do that is because we create an identity. So A is equal to 25 sine 2 theta. Well, that is easier to take the derivative of if you recognize it, because you don't need to use the product rule. So let's talk about A prime. A prime now will be equal to 25 cos 2 theta times the derivative of the argument, which would be 2, times 2. So A prime equals 50 cos 2 theta. Well, what's the strategy then? You want A prime to equal 0. When does 50 cos 2 theta equal 0? So dividing both sides by 50, you've got cos 2 theta is equal to 0. And looking at the cosine curve, you know cosine is equal to 0 at pi over 2. So that means 2 theta is equal to pi over 2, which implies theta is equal to pi over 4. Our conclusion is that by making this angle pi over 4, you're going to maximize the area of this triangle. The last question I'm going to do, number 4, is a triangle with center 0, or a circle with center 0, has these as its vertices. 2 letters on the edge of the circle, and then center O. And they tell us the radius is 5. So I've drawn in the diagram, and I've also identified this angle as theta. We're going to change that in a moment, I think. And this is going to be the height, and this will be half of the base. So in order to look at this a little bit easier, I think what we'll do is we'll make this angle in here theta. That implies this angle right here 2 theta. But let's call this one theta right now. And we can say the sine of theta equals x over 5. So theta, so x equals 5 sine theta. And likewise, we can say that cos of theta is equal to h over 5. So h equals 5 cos theta. When we're finding the area of the triangle, we will say the area of the triangle is 1/2 the base times the height. Well, in this case, the base is 2x. So as we substitute that in, 1/2 times 2 is just x times h. So area is equal to x, 5 sine theta, times h, 5 cos theta. So area is equal to 25 sine theta cos theta. We could do the exact same thing we did with that previous question, but what I think I'll do is show you how you can use the product rule on this one. So there's the first and there's the second. So A prime equals first, 25 sine theta, times the derivative of the second. The derivative of cos theta is negative sine theta, plus second cos theta times the derivative of the first, times 25 cos theta. So we've got A prime to be equal to, and I'm going to simplify this way, 25 cos squared theta minus 25 sine squared theta. So A prime equals, common factoring out the 25, cos squared theta minus sine squared theta. Well, that's an identity. That's equal to cos 2 theta. And we're back to where we were before. I'll continue this question up here. When does A prime equal 0? When 25 cos 2 theta is equal to 0. So cos 2 theta equals 0 divided by 25. Cos 2 theta is equal to 0. According to the cos curve, theta must be equal to pi over 2. So that would suggest theta is equal to pi over 4, but in this diagram, we're not interested in how big this angle is. We're interested in how big this angle is. So if 2 theta is equal to pi over 2, you're going to maximize the area of that triangle. I hope that video helps.